So we're going to start today by introducing two new concepts, which we'll see more of for the rest of the course, and also both of these, well, at least the first one will be very useful in the homework. Okay, so let me start with what a Cartesian product is. So notice that when we defined a set, the order that we list the elements doesn't matter for a set. Okay, this wasn't something that I made a big point of, but certainly the set 1, 2 is exactly the same as the set 2, 1, right? And I mean, the reason is we say two sets are equal if their elements are the same. We don't care how you list them, okay? So this is fine, but it's also obviously useful to, have collections of elements where you do care about the order, okay? So here's the first definition makes this precise. So an ordered pair is an ordered list of two objects. Okay, so it's usually denoted by, instead of brackets now we use parentheses, so denote AB. And so what this means is that when I say I have AB equal to CD, this is true exactly when A is equal to C and B is equal to D. Okay, so notice this isn't true for this statement about sets. We have to put in these extra conditions. Okay, so then another definition now, if we have two sets, so let A be sets, we can make a new set, which is called the Cartesian product. Which is, and it's usually denoted by A cross B. So it's just the set of all such ordered pairs. So it's the set of all ordered pairs. So I'll write it this way. So A cross B is defined to be all ordered pairs where A is in A and B is in B. Okay, so just as a, again, sanity check / my favorite game, let's check, is it true or false that A cross B is equal to B cross A? Okay, so I'll pause here. Okay, so this turns out to be false. Okay. And the reason is, well, we've exactly, put in these conditions where the order matters. Okay, so again, if I want to say something's false, I just come up with a counterexample. I don't know, A can be the set containing 1, B can be, I don't know, the set containing a tree. Just for fun. Okay, and then, well, what's A cross B? Well, it's the set containing a single element. It's one tree. And on the other hand, B cross A is equal to the set containing tree 1. And we've said that those are not equal, okay? Because trees aren't equal to 1. Okay, so in general, I think, well, there is an example where this is true. So which is that just that if A is equal to B. So we've seen, but that, comes up quite naturally in mathematics, or especially in calculus. So we see if you're looking at, R could be our set, and then if you want to make the Cartesian product R cross R, or sometimes people write R squared, well, this is the same. You can switch the order here and get the same set, and then you get the usual xy plane, maybe I'll say here, A, B, where the points in the xy plane are precisely the ordered pairs of real numbers. Okay, so this will kind of come up in a couple ways in this class. So for on the homework, you'll see that Cartesian products allow one to define equivalence relations. These will be important later in the class, and I put a number of problems about them on the homework. In our setting, we're going to use them, or I guess just in this lecture today, we're going to use them to understand functions. Okay, so let's recall from calculus. What is a real valued single variable function? Okay, I'm gonna pause here, just think about what your answer would be to this question. Okay, so one way to describe it is that it's a rule which assigns to each x. Well, so what x is usually, doesn't have to be an arbitrary real number. It's some element, some real number in the domain of your function, which might be smaller than the entire real numbers. A unique f of x, which is also a subset of the real numbers called the image. So this is the domain, and this is the image. And I haven't said anything about whether this function's continuous or not, so we don't have to worry about any of that. The only important thing that we care about is that the function spits out a unique element in the range. Okay, so yeah. All right, so let me give you an example. Well, f of x, the best example, f of x is x squared. So x, another way to write this is just x maps to x squared. And I'll even say this is the notation, or the expression I'm going to use, probably without even thinking about it. So I think of x as mapping into x squared. And then if we want to check that it's a function, you have to check that, given an x, x squared is a unique number, which it is. Okay. All right, so we can think of, maybe I'll just think of f as a machine. Right, this is kind of how we think of functions. The input gets sent in to the machine, some sort of machine, and call it f. And so this is x, and then we output, the function f of x. All right. So now what we want to do is to bring Cartesian products into this description. And the way that we can do this is we can think of input, output as an ordered pair of real numbers. as an ordered pair, x, f of x, which is in R cross R. Okay, so if you think about it, this is exactly what we do when we graph the function. When we say f of x is x squared, and then I say, okay, I'll draw the graph on the xy plane. Well, what I'm doing is I'm exactly pointing out, picking out the points in this Cartesian product that satisfy this description. So this would be, x squared. So the points that live on the graph are the points that, well, it's the input of the function and then the output of the function. Okay, so now I'd like us to kind of shift our perspective a bit. And instead of thinking about f as a function, we instead think of a function, or think of f, as a subset of R cross R with special properties. Okay, so we've seen that, essentially this function determines the graph that's in R cross R. But now I want to say, well, actually the important thing is the graph. Okay, and then that's the way that we'll actually be able to generalize the definition of function to other settings. So what do I mean here? So let me give you a new definition of function. So new definition of f, instead of, this unique rule, I'm just going to say it's a function, which we can still have, it's good notation to have f going from R to R, is a set of ordered pairs such that, well, I'm going to say pause. What is the condition on ordered pairs that this function should satisfy? Okay, so let's think. The only condition we had on f was that if I gave you an x, there was a unique f of x. Okay? So translating that condition into ordered pairs says that if I have xy and xz, now these are in f, so they're elements of f, then y is equal to z. Okay, this is exactly saying that if I give you the same input and the outputs, it gives you two outputs, they have to be the same. Okay? So you've all seen this before. So for the graph, this is called the vertical line test. Okay, so here's the picture. If I had this graph, or alleged graph of a function, this is a perfectly good subset of R cross R, but when I draw my vertical line and I'm getting xy and xz, and y is not equal to z here. Okay, so this is the failure of the vertical line test is exactly failing this condition. Okay, so let's do some more examples. Okay, so the first one, we already said it was f of x is x squared. So I'll just write it again. We now think of it as x squared, where x is in R. Okay, contained in this Cartesian product. But there are also, you can just choose kind of random other subsets of the Cartesian product, as long as they satisfy this test. So from our perspective, here's a perfectly valid function. Okay, this is also contained in R cross R. So this maybe isn't the most interesting function. I mean, it's just your taste. So this sends 1 to 2, sends 3 to 2. And notice there's no problem with the y coordinates being the same. I mean, this happens in this example too, for 1 and minus 1. But for each x value, there's a unique y value. So this is a perfectly good function. Okay? I mean, the graph of it isn't that interesting, but, why do we need to be constrained by that? So here's an example of not a function. Oops. Right, and the reason here is, well, I draw, I've given this number of ordered pairs, but I've put in something which fails the vertical line test. So, this vertical line test doesn't need a continuous, graph drawn. It can just be 2 points like this. That's itself a failure of the vertical line test, and that's what is going on in this example. Okay, so the important thing is that functions don't need to be given by formulas. And in fact, most functions that a random function will never have a kind of nice formula associated to it. So it's better to just kind of give up on that perspective, at least, for this class. Okay? So now we ask, well, why do we need R at all in this discussion? Well, the answer is we don't. We don't need it at all. So let me just give you now the general definition. So a function, a function a to b between two sets A and B is just a subset of the Cartesian product. So it's a subset of A times B, and it just satisfies the same condition. So if AB is in F, AC is in F, then B is equal to C. So in this setting, we say that A is the domain of F, and the range of F, or the image of F, is defined as the B in B, where there exists an A in A, so that F of A is equal to B. So the reason we want to do this general definition, so the goal of this definition is to capture the essence of many examples at once. Okay, so we've seen, it's useful to have, functions that go from R to R. F of x is x squared. That's a good function to know. But it's also useful to have maybe a function from the natural numbers to the real numbers, which then is, f of n goes to n plus 1. So actually this is, say this will come up later, right? This is just the way that we're going to define a sequence. So this is just a sequence of real numbers. something like 1. So I guess, oh, in this case it went 2, 3, 4, ... So you can also have, functions that don't involve sets that come up in math at all and are still pretty useful. So here's one example. So I could have the function which I'm just going to denote by number. It's going to input it as it sets the UChicago students. So my S is a UChicago student. That's a good set of people. Okay. And the output is going to be the natural numbers. And the way that I'm going to define a function is it's just going to input a student, and then it will output the student number. Okay, so the UChicago student number. So first, let's just check, is this a function? And I'd like people to pause and just kind of think about your, how you would explain or justify this. Okay, so let me pull this up. So I claim it is a function because I think students have unique numbers. Okay, and that's exactly what this being a function needs. Okay, so what's the range? I mean, we know the image. The image is just all UChicago students. The range, I have no idea, right? This is usually something that's hard to figure out, but we definitely know it's a subset of the natural numbers. And this this oftentimes when I write a function from A to B, so, I know that it goes to the natural numbers. If you actually wanted to pinpoint what, subset, what the actual image of is, that's hard. But I can at least tell you, where the things live. Okay. So let me give you another example, which will let me draw my favorite figures. So I could have, a point, my sphere, my torus. Okay, I'll do my tree. I'm going to make it autumn tree. And it's going to go to just, 1, 2, 3, 4. Okay, that's my set A. That's my set B. Okay, and I don't know. Let's just say W of a point is 1. W of the sphere is 2. My donut goes to 1. And my tree, I don't know, goes to 3. Okay? So now you might say, well, you might question why I'm bothering to do this function, but why not? So I just want to point out that this is not a subset of the xy plane, obviously. It's a subset of, this set times this set. But I'd still like a way to get a graph, okay? But we still want a graph. Okay, we're not going to be gaining any more information, but it's going to help visualizing it, which is, why people like graphs of functions, of real valued functions in the first place, is that, it lets you see what this function's actually doing. So the way that you can do it here is, well, you put your set A on one side. If I was clever, I would know how to copy paste things. Maybe, by the end of the class, you will see me grow in my technological abilities. And so here I have my set A, here I have my set B, and the way that we say what f is doing is we just draw arrows between the input and the output. So if I did this correctly, this will go here, this would go here, and this would go here. Okay, so we can, in this way, you kind of see where all the elements of A are going. You can think of this function as, casting some sort of shadow. So casting a shadow of A in B. So you imagine standing on this set B, looking above you in the set A and seeing what, seeing what you see in the set A that gets sent to you. So this function gives two natural ways to relate subsets now. So if C is a subset of A, then I can say f of C is, the shadow of C in B. So in other words, it's the things that are in B that are hit by elements of C. So f of C are the B in B. So this is called the image of the set C. There exists some element of C so that f of C is equal to B. Okay, so let me just mark, this is the point, this is a subset of B, okay, by this condition. Similarly, you can look at a set B, or I'll say if D is contained in B, then I can look at the things above D. So this is the shadow over D. In other words, it's just precisely, so F inverse of D is, it's the A in A, so that F of A is in D. Okay, so this is now a subset of A. Okay, so I'm just going to point out two more things. Okay, so the first is that, let me give this as an example. Maybe I'll just say it as a question. What is f of A? Okay, so pause here. Okay, so this is just the elements B and B which are hit by an element of A. So this is just the range of F. Okay. So one other thing to now worry about, or one other thing to point out, is if I write F inverse of D, well, I even said F inverse. It's bad of me to say it. So this is called the preimage of D. The point to make is that F inverse may not be a function. Right? So you can even, so recall from calculus, not every function is invertible. And we've seen, the usual example of this, f of x equals x squared is an example. Okay, so when I write this notation, I'm saying the things that get sent to A, or get sent to D, but I'm certainly not saying that this is the image of D under some inverse function. Okay? Okay, so I think I can stop there. So, thanks.